Right. So today we have two talks. The first by Steffen Sagave at Radboud Universiteit in Nijmegen, who will speak on logarithmic topological cyclic homology.
Yeah, thanks, and thanks for having me. So this is joint work in progress with John Rognes and Christian Schlichtröll, and I will briefly tell you how I structure the talk. I will first explain why we are doing this, then I'll explain what we are doing, and in the end I will explain how we are doing it. I'm saying this in beforehand because there will be some undefined terms on the blackboard, and my aim is to resolve this later on. So if you see words that you don't understand, please stay patient. So the motivation for this comes from algebraic K-theory. So when I'm trying to understand algebraic K-theory, it's good to have both structural tools, such as localization sequences or devisage, and computational tools, such as trace maps. And the localization sequences that motivate what we are doing here, they come from work of Quillen. So Quillen defined localization homotopy cofiber sequences of K-theory spectra already back in the day when he introduced algebraic K-theory, even in bigger generality, and so this gives a long exact sequence of K groups. So this is about K-theory of discrete rings, but there are also localization sequences for the algebraic K-theory of structured ring spectra, and one that is of particular interest for this business is a localization homotopy cofiber sequence that was constructed by Blankenberg and Mandel, and I think the paper appeared around 2009. So there's a localization sequence relating the K-theory of the P with the algebraic K-theory of the P-complete Adams summand. So P-complete Adams summand is spectrum whose homotopy groups are ZP and then a polynomial ring on a generator V1, where the degree of V1 is 2p minus 2. And the third term in this localization sequence is the algebraic K-theory of the periodic companion of the P-complete Adams summand. And I'm drawing these two cofiber sequences in this way because you can now fill something in. You can also look at the algebraic K-theory of this gadget and then mod P, and there is a transfer map in this direction and a map in this direction, and you can look at the K-theory of the periodic theory and mod out P. There's also a transfer map. There's a map like this, and then you can take the cofiber of this map and get something that fits in here, and then you can also take the iterated cofiber down here. So you can also fill something in here. And then you have something that sits in a diagram of cofiber sequences of which some terms are OK and some terms are not. But what turns out, and this is an observation.
Instead of Q in the upper right-hand
Oh,
corner.
sure. That's bad. Yeah, thank you. So what turns out is that this term here is interesting, and so this is something that John Rognes and Christian Arsoni studied in a preprint that I think appeared around 2009, but I think some of this is even older. And they gave this object a kind of optimistic name. They called it the K-theory of the fraction field of LP. So it's a K-theory of the fraction field of topological K-theory, and what they did is, based on this rather indirect definition of this K-theory term, they made some computations. So this is Sony, Rognes, 9. And so what they did is they computed the V1 homotopy of this K-theory of the fraction field of topological K-theory for P at least 5, and I think in degrees at least 2p. And the answer of this computation, I could in principle write it down, but it's not so relevant for this talk and a bit too complicated. But what these computations indicated is that this is a potentially kind of very interesting object, because the K-theory is somewhat accessible, and it shows all kinds of other phenomena. So they kind of made conjectures about the Galois cohomology of this, and I think also a Galois descent spectral sequence. And so in total, it behaves like a two-local field of mixed characteristic 0 PV1. So it's a potentially interesting gadget, but it's of course highly unsatisfactory to define an object by defining its algebraic K-theory as as a kind of iterated homotopy cofiber. So the real question is, what is this fraction field of topological K-theory? And yeah, to also motivate the answer we are now giving, it's good to switch over to topological Husserl homology. Luckily, topological Husserl homology also has localization sequences, but this is taken to be with a little bit of care. So you can also form localization sequences, so homotopy cofiber sequences of topological Husserl homology spectra, but you don't have the same ones as you have for algebraic K-theory. So one instant that is relevant for this example here is there's a homotopy cofiber sequence relating the topological Husserl homology of Fp. And there's a transfer map to the topological Husserl homology of Zp. And now, from what you see above, you would hope that you put the topological Husserl homology of Qp there, but that doesn't work and doesn't give this sequence. So what you should do instead is define a certain relative term, and there are different ways to do this. So it's often denoted by Zp bar Qp, and one construction of this relative term is due to Hesselholt and Madsen, who did this in their work on the algebraic K-theory of local fields in much bigger generality. But kind of you can't take Qp here. And maybe this is something I should have said. This is, of course, also the obvious guess that doesn't work here. When you kind of look at this diagram on a very optimistic sunny day, then you think, oh, why not taking the K-theory of LP and then P inverted? So that's the obvious guess, and this guess doesn't do it. Otherwise, my talk would already be over, which would be a bit too short. So this cannot work because the K-theory of that one would be a module over the K-theory of Qp, and kind of the calculations say that this doesn't work. Okay, so there's such a localization sequence. There's an analogous localization sequence, again, kind of with the same problem for the vertical one. So there's one relating Zp, the topological Husserl homology of LP, and the topological Husserl homology. And now there's again a relative term. So this one was constructed by Blumberg and Mandel in a kind of, I think the paper appeared only in 2020, but this is more a publication delay. So these localization sequences exist. And one feature that they share is that when you start calculating the homotopy groups of these somewhat artificial terms, then you have logarithmic differentials in the homotopy of these terms. And this led, I think, John, perhaps also Christian Ossoni and Lars Hesselholt, to the conjecture that these relative terms should have something to do with logarithmic geometry. So, and then you kind of can optimistically hope that you can maybe define these relative terms by defining a certain logarithmic object whose topological Husserl homology then gives this answer here. And you can even be even more optimistic. You can hope that you can write down a logarithmic object that realizes this conjectural fraction field. So the conjecture is, and I attribute this to John, and this is fair because he can say no if he thinks this is inappropriate. So the conjecture was the fraction field of topological K-theory can be realized as a logarithmic ring spectrum, whatever this should be. And there was indeed some positive evidence for this. So kind of John started with this, I think, the first paper appeared in 2009. And so he found a notion of a logarithmic ring spectrum that was well suited to deal with this case here. So there was a notion of a logarithmic ring spectrum so that you have a localization sequence of this type and the expected logarithmic differentials in the homotopy. It's not at all clear that this logarithmic term is equivalent to this one, so this is what we expect, but writing down an equivalence is a subtle thing. And in later work, John, Christian, and I cooked up somewhat more sophisticated version of logarithmic ring spectra, where we were also able to define interesting logarithmic structures on examples like the atom summand, and where we had a homotopy co-fiber sequence of this shape. And again, the calculations kind of confirmed the behavior that we were hoping for, and it had all kinds of interesting properties. But in the work we did back then, we were not able to actually realize this fraction field, which was kind of somewhat the most interesting thing. And yeah, one reason for this was that we were sticking to a notion where we had to use E-infinity structures and not EK structures, and this is one of the reasons why this didn't work out. And after kind of changing the definitions in a reasonable way, we're now finally arrived at a notion where this works better. And yeah, this is now, okay, I just erased it. And now come to the what part of the talk. So I write down the theorem. And I put optimistically, so the preprint isn't yet fully finished, but mostly finished. So I'm optimistically writing a 25 here for indicating that it will appear soon. And one way to phrase it is the following. There is a commutative square of pre-log E2 rings, and so consists of the atom summand, and I'll take the p-local version, not the p-completed version, but the difference, we would have the same here. So we can, it's an E-infinity ring, we can view it as an E2 ring, and we can also view it as an pre-log E2 ring. And then it comes with a map to this pre-log E2 ring atom summand with a pre-log structure generated by P. So this is something I'll define. And the same here with the pre-log structure generated by V1. And then there's also a pre-log structure generated by P and V1. And it's this pre-log E2 ring that we think of as a model for this fraction field of topological K-theory. And well, of course, everyone is free to define anything. So what gives us evidence for this? The evidence for this is the following. So it's this is inducing 3 times 3 diagram of horizontal and vertical homotopy co-fiber sequences. And this is now up to a shift, matching the diagram that I wrote down for algebraic K-theory in the beginning. So we have THH of L here, and then we have a certain logarithmic THH of L with this log structure here. And here we now have a suspended copy of THH of L mod P. And here we have THH of L with a prelog structure generated by V1. And here we have the suspension of THH of Z localized at P. Here in the middle, we have the topological Hochschild homology of this fraction field. And yeah, now I have to put in the remaining terms. So here we have the topological Hochschild homology of, now I shouldn't get confused. So here we have this equal L mod P, and the prelog structure generated by V1 survives. Here we have THH of Z localized at P, and still have this prelog structure generated by P. And the last term, there's of course a suspension, and the last term is a double suspension of the topological Hochschild homology of Fp. And this is exactly the shape of diagram that we would expect from this K-theory motivation. So in terms of topological Hochschild homology, this gadget we define here exactly sits in the localization sequences it's supposed to sit. And the sentence that makes the theorem is not yet finished. It's even better. So it's a diagram of cyclotomic THH of L modules. So what the theorem in particular says is that all these objects in this diagram here enjoy cyclotomic structures in the sense of Nikolaus-Scholz, and all the maps are compatible with them. So the corollary is we get the same diagram for topological cyclic homology in terms of topological Hochschild homology. So this is very good and kind of justifies the title of the talk. And yeah, you can also kind of think of the topological cyclic homology of this middle term of this fraction field then as something that's coming pretty close to the K-theory that we are after. We're not claiming to have any direct trace map. So this is something that's not at all clear. But then again, for many other purposes, having the TC of this fraction field may be as interesting as the algebraic K-theory, kind of in view of kind of fancy cohomology theories that you can derive from TC. Yeah?
And then something with brackets, that's logarithmic THH?
That is the logarithmic THH, yes. And that's something that's part of the how talk section. This is something that I now explain. So this is a form of logarithmic THH that comes kind of with the cyclotomic structure. Yes?
How specific is this to the atom summit? Like BPNs and more GIs?
We have, so for BPN, that's also working well. Then it's just a bit hard to draw on the blackboard because you then kind of get multiple directions, but you get a kind of higher dimensional cube of homotopy cofiber sequences where the THH of BPN is here, and then here's a appropriate suspension and everything in between. So this is something that we handle as well, and that's of course very kind of interesting. And you can do the same, of course, for KU instead of the atom summand. So there's all kinds of variations possible, but I found it clearer to just give one example. Regular is actually not that relevant. Okay, evenness plays a role. I'll explain it in a second. Okay, to now come to the how part, and I should tell you what the definitions are that we're actually using. So one definition that motivates all this is that of a discrete pre-log ring. So this is what people use in logarithmic algebraic geometry as a building block for logarithmic schemes. So a discrete pre-log ring, it's often written AM, but it really kind of consists of more data, is a commutative ring A, a commutative monoid M, and a monoid homomorphism from M into the multiplicative monoid of the ring, and this one we call alpha. And for what we do, I should make the quite obvious remark that this monoid homomorphism is, of course, the same data as its adjoint from the integral monoid ring of M to the A, then viewed as a homomorphism of commutative rings. So the examples you should have in mind is something like, maybe you just take M to be the trivial monoid, that works fine. Or you take an element X in A, and then you get out a map from the free commutative monoid on one generator mapping to A, that sends a generator to your X. And it's another example that works is you take M to be the unit and take the inclusion of the units in A. So these are all relevant examples. As the name pre-log strongly suggests, there's a notion of a logarithmic ring. That's also useful in this business, but I'll skip it for this talk. So there's a log notion in the back. That's a kind of normalization condition, but I won't go into this. So why is this useful? Well, kind of you should think of this monoid data and this homomorphism as specifying certain elements in your ring that you may want to eventually invert, but instead of inverting them, you introduce a bookkeeping over these objects. So and this allows you to define something that sits between a ring and the localization of the ring at certain elements, but you don't go all the way to the localization and rather remind what this is, kind of remember what this is. Okay, now this is a thing that we want to generalize to structured ring spectra, but we also want to generalize, find a notion of topological Hochschild homology. So I'll briefly explain to you how you can define Hochschild homology for these objects. Well, if you kind of define the Hochschild homology of a ring A, you can do this, at least as a homotopy theorist, by taking the realization of the cyclic bar construction of your ring A. So this is a realization of a cyclic object that you get by taking higher and higher tensor powers of your ring A. So I only write 2 copies here because I'm running out of space. So this is something. This is one possible definition of Hochschild homology, and this one is very nice. And when you are interested in the cyclic bar construction of such an integral monoid ring, then it's also not difficult to see that you can also write this as an integral monoid ring of the commutative monoid you get by taking the cyclic bar construction of this commutative monoid, just taking the product. So this is useful, but the definition of Hochschild homology for these discrete pre-log rings needs one more subtle ingredient that's not completely obvious. So the definition I'm giving here is also due to John. So there are other possible definitions that are good for other reasons, but from the point of view of homotopy theory, this definition here is very appealing. So what John defined is, he defined the Hochschild homology of a pre-log ring A, comma M as the following object. So you take the Hochschild homology, I'll keep the realization outside. So you take the cyclic bar construction on A, then you tensor over this integral monoid ring of the cyclic bar construction of your monoid. And kind of I explained how you get a map from here to here. And then there's one more ingredient, and this is the integral monoid ring on the replete bar construction of M. And this is the one term I still have to define. This is done as follows. So when you have a commutative monoid, you can always take its group completion. And when you take the cyclic bar construction on the group completion of M, then you have an augmentation map down here. The point being that this here is a commutative object, so you can take iterated multiplication maps down here. So we have this diagram here, and then you define the replete bar construction of M to be the pullback of this diagram. And this is the one that gets in here. And then, of course, you need a map. But that's easy because by the universal property of the pullback, you get a map here. And then you get out this diagram. OK, this is nice. But maybe I should briefly explain why this is a wise choice of a definition, because kind of it looks a little bit artificial, and there's a nice way to see that this indeed has something to do with logarithmic differentials, and this is kind of the most elementary case. If you look at the cyclic bar construction of the natural numbers and the replete bar construction of the natural numbers, you could also say commutative monoid on one generator, and then the cyclic bar construction of its group completion, also known as the integers, then you can wonder what this is. And this turns out to be a disjoint union of a point and then big disjoint union of circles. And kind of there's a weight decomposition by multiplying together the weights. And then the replete bar construction, this is a disjoint union of circles, but there's one circle more, now also in degree 0. Well, and this here is just a disjoint union of circles where there's one circle for every integer. And I could use this notation to say that it's just a big disjoint union. You can also say something about the circle action, but that's not so relevant for us now. And well, if you now look into what's the integral homology is of this, then on this side you get a polynomial ring tensor and exterior algebra on a generator in degree 1. So this sits in homological degree 0 and degree 0 of this grading. This sits in homological degree 1 and degree 1 of the grading. And if you map here, well, then it looks a little bit differently. So there's still generator in degree 0, but now the generator in homological degree 1, that already starts to come to life in degree 0 of the grading. And the map that you have here sends the class dx to x times d log x, while it does nothing with the x. And it's kind of this addition of this one circle in this degree here, which kind of makes this change of going from the cyclic bar construction to the replete bar construction, and then makes sure that you kind of have the desired effect on the homotopy groups of topological Hochschild homology in examples. And well, besides matching this example, there are also other kind of more sophisticated reasons why this is the right notion of Hochschild homology for logarithmic rings. Yes?
If I have this image of the cyclic bar construction as points on a circle, and when they collide, you multiply them, etc. Do you have a similar picture for this plate bar construction?
Well, since it sits inside here, I think you can just steal it from here. So it just kind of adds more in from the group completion.
So it adds certain things.
Exactly. So it maps. It adds these things from the group completion that that kind of in the augmentation sit over the original monoid. So your picture is still completely valid for the cyclic bar construction on the group completion, and then you just restrict to certain components of that. Okay. So far for the Hochschild homology. Now, what's the definition of pre-log EK ring? Well, if you kind of look at this definition of discrete pre-log rings and want to generalize it to structured ring spectra, then it's actually not so super difficult to come up with the first suggestion. So the kind of first idea is maybe, well, you stay perhaps commutative. You take, say that a pre-log E infinity ring is, well, then triple AM alpha bar with a E infinity ring, M an E infinity monoid, and then you take the spherical monoid ring on M and map from here with alpha bar to alpha. So you take a map of E infinity rings here. So this is a pretty obvious definition, and it actually this works well for Heisenberg-MacLane spectra. So kind of the Hochschild homology or topological Hochschild homology with kind of this definition is interesting for Heisenberg-MacLane spectra of commutative rings and pre-log structures in this context. So there's nothing wrong with this, but for treating cases like the Adams summand and other structured ring spectra, it doesn't work so well. So this was the first idea. The second idea is maybe kind of in homotopy theory, as you all know, we can work less commutative than E infinity. So the second idea is to take everything that was E infinity here to be EK, and this of course also was an E infinity map, so this should then also be EK. This is fine, allows certainly for more examples, like kind of the BPN case would never fit into this E infinity setup, but it's still super hard to produce interesting pre-log structure generated by positive dimensional homotopy classes. And the real problem underlying this is that, well, the homotopy groups of a structured ring spectrum A, this is a graded commutative ring. And for producing pre-log structures generated by positive dimensional homotopy classes, it turns out to be wise to take this grading into account. And in the papers that we published several years ago on this topic, we had a solution to this problem and took the grading into account, but the solution was only really working in the infinity case and still a little bit too rigid to include the examples we really care about. And one reason now to deal with this grading is the following observation. So when you take an E infinity base ring R, then you can look at R module Thom spectra. So there's a Thom spectrum functor from spaces over pick R to R modules. And one way to define it is just to take a map from X to pick R, compose it with the inclusion of this infinity groupoid pick R into the category of R modules, and take the co-limit over this. So this is now well understood. And this is a symmetric monoidal functor in the infinity categorical sense, but it's even more than that. It's also left adjoint functor, and because it's symmetric monoidal, it induces a functor on the associated categories of EK algebras. So the adjunction is, of course, already there before passing to EK algebras, but it's that adjunction we really care about. So you have EK algebras in the category of spaces over pick R, and then you take the associated Thom spectrum, and then you land in EK R algebras, so in EK algebras in R modules, and there is this right adjoint here. And for some reason, the right adjoint is by far not as kind of popular in the literature as the Thom spectrum functor is, but it's super useful for our purposes because of the following. So in this obvious approaches to generalizing discrete prelog rings to structured ring spectra, I advocated that you should use the spherical monoid ring. And the Thom spectrum, if we work based over the sphere, this one, of course, generalizes the spherical monoid ring. So if you just take a monoid and take the constant map to pick S and then take the Thom spectrum, then we get back the spherical monoid ring. But here we allow for more general input data, and this is such maps to pick S in the case where R is S. And this right adjoint, this one, yeah, it, in some sense generalizes the passage from a commutative monoid to its underlying multiplicative monoid. So what I mean by this is, if you look at this right adjoint as an object over pick S, including its multiplication, then you can still read off the underlying graded multiplicative monoid of your ring spectrum from the omega S of your ring spectrum. And what goes in here is that, of course, pi naught of pick S is Z, and pi 1 of pick S is plus minus 1. So the point being that this Z here takes care of the Z grading that your homotopy groups have, and this plus minus 1 takes care of the sign action that you need to make sense of a graded commutative monoid. So if it becomes commutative by accident, then you made something wrong, obviously. And now the only thing what you need to do is you just need to strongly believe that these two play, that this adjunction plays the role of the junction between an underlying multiplicative monoid and the integral monoid ring, and then you arrive at a good definition. And to be on the safe side, I'm now writing down what I just said. So our definition is then prelog EK ring A psi alpha bar consists of an EK ring A, EK map psi from M to pick S. So this is an object in this category of EK algebra objects in this slice category. And finally, and a structure map from the Thom spectrum of this map psi to our A, and this of course is also an EK map, a little surprising. And by what I said about the adjunction, you could trade this map alpha bar into its adjoint, but that doesn't make a big difference. Okay, so this is a definition that looks good, but now we need examples.
So
and
this right adjoint up there, am I understanding this right, that the sense R is the sphere, it sends a spectrum to a space such that pi naught of the space is roughly pi star of the sphere?
It's more sophisticated. It sends it a spectrum, a ring spectrum, to a space over pic S, and you have to assemble the path components of the homotopy fibers of this augmentation together to get the to get back the homotopy groups.
If I input a spectrum,
Yes?
it gives me a space with a map to pic S.
Yes.
What's pi naught of the space?
That's a quotient of pi star by the ±1 action. So then you kill, if you just look at the space without the augmentation, then you kill the ±1 action, which is fine for some purposes, but not for all. Okay, examples. So one example that is particularly useful is the following. We do the following. We start with the natural numbers, multiply by some natural number d, and land in the integers, which we can identify with the second loop space of BU1. This is all E infinity. Now we take the inclusion of BU1 into BU. This is only E2. This is a pity, but there's nothing we can do about this. This we identify with Z times BU. And from here, we go with the complex J homomorphism into pic S. So, and this is a very interesting gadget. So let's call this composite psi 2D. And of course, the 2 is here because it sends the generator 1 here to the path component of 2D here. This is why there's the name. So what follows from this is that the Thom spectrum of this thing, this is an interesting spectrum. So this is an E2 ring. That's good. And the underlying E1 spectrum is the free E1 ring on a 2D dimensional sphere, but it enjoys an E2 structure, and this is good. And this one, this psi 2D, we would like to use as the ring spectrum coordinate here. But then, of course, we still need to construct structure maps. And for this, it's very useful to make an observation that appears in a very detailed form in a paper by Oscar together with Sander Coopers and Søren Galatius. And this gadget here comes with an E2 cell structure. So this has an E2 cell structure with cells in even dimension, dependent on D, also say exactly where the dimensions of the cells are, but just kind of as a rough approximation, we get as a consequence when A is an even E2 ring, so homotopy groups only concentrated in even degrees, and we pick some homotopy class X in even degree of A, then the kind of obstruction theory tells us that we get an induced map alpha bar from the Thom spectrum over S of this psi 2D to A that is hitting the class X. So any even homotopy class kind of can be hit by a pre-log structure this way. And yeah, of course, it's highly non-unique. So we can't make any statement about uniqueness. But in the examples we care about most, logification, which I didn't tell you about, takes care of this. So we can show that that in cases like the K-theory spectra, if you do this, then the topological Hochschild homology is insensitive to this choice. So nothing goes wrong here. So in this with this procedure, we get as examples for pre-log E2 rings things like L with pre-log structure generated by V1 and L generated with P and many more of those. And the definition now differs from the definition that Jon Christian and I used back in our old papers, but in terms of topological Hochschild homology, the answer is still the same. Yeah, and what now to do about the fraction field? Well, you can more generally construct an E2 map 2D1 to 2DR from R-fold Cartesian product of this to pick S. And also in this example, you will have an even cell structure on the associated Thom spectrum. And then there are just a few more cells. But you can exactly do what I did in this example. It's just with a little bit more complicated bookkeeping. And the examples that result from this give you things like, yeah, the fraction field we are after. And the example that Kais already mentioned, you can take BPN, which luckily is known to be an E3 ring even, with the pre-log structure generated by P, V1, and all the way up to Vn. And so these are very, very nice examples. Of course, when you look at this, you think that it's a pity that it's only E2 and not perhaps E3 or even better, but there are limitations to this. So like this map that I wrote up there, which is an E2 map, can in general not be improved to be an E3 map. So they're just obstructions. And also for this pre-log structure, so you can kind of do logish constructions to them that produce LP for you. And LP can only be an E1 ring, and that puts up some limitations of what you can expect. Okay, now I should, to at least define everything that I had in the theorem in the beginning, tell you what the topological Hochschild homology of these log objects is. And there we actually run into a problem, and this is the following. So what you can still do is, as before, well, we have now this map Xi from M to pick S. And from the motivation I gave, it's clear we care about the group completion. And group completion of EK spaces works well, so this is all fine. Pick S is by its very construction group-like, so you get an extension here. So this far things work well. But now in the motivation I gave you, you would form now the cyclic bar construction on the monoid again, on the group completion of the monoid, as we did before. But in what we did before, it was essential that the iterated multiplication maps give you an augmentation of the cyclic bar construction. And this is now going wrong because, well, we don't ask for commutativity. And for general, say, E2 space, you don't have these augmentations. So this would need extra structure that we don't want to impose here. So this looks like a problem because, yeah, we're missing the augmentation to define the replete bar construction, and we're also missing the augmentation to pick S to form the Thom spectrum again. And luckily, there's a solution to the two problems, or there are two different solutions to the problems. And the trick is now to do the following. Well, we have the cyclic bar construction on the group completion here. But now we can, of course, say for the map 2 here, we solve the problem by just switching orders. It's fine to take the cyclic bar construction on pick S pick S is E infinity. So from here, we go down to pick S. So that's good. But the bigger problem is that we're missing this one here, so that we can't form the replete bar construction. The trick for this is we take the zeroth Postnikov truncation of this group completion. So in other words, we just go to the pi naught of the group completion. Since we impose it, since we ask it to be an EK space, and well, I never said this, but we want K to be at least 2. That's maybe not super surprising. So, but when K is at least 2, then this one turns out to be a commutative monoid. And then again, we kind of have our old trick of augmenting it by iterated multiplications. And then we can pull back the map that comes here from pi naught of M and form the pullback. And this now gives us a version of the replete bar construction on M. But it is not the same in general. So if you kind of do this for a general E infinity space, then you could also take this construction that up here that wouldn't work for an general EK space. And this answer that we produce here is not the same as you would get for a general E infinity space. But luckily, in the examples we care about, it turns out to be the correct answer. And yeah, with this construction, we get this this replete bar construction, and we also get it as an object over pick S. Of course, we sacrifice one layer of commutativity along the way. So when M is EK, then so is its group completion, but forming the cyclic bar construction only gives us an EK minus 1 object. This is a price we have to pay, but this composite map is still an EK minus 1 map, so this is fine. And then we can finally define the topological Hochschild homology of A, Xi, and alpha bar. And well, we define it to be the relative tensor product, where we take just the topological Hochschild homology of A. Then we take the topological Hochschild homology of the tome spectrum of this map Xi. So this now takes the role of the Hochschild homology of the monoid ring on the cyclic bar construction of the monoid. And here we can exchange the tome spectrum with the THH. And at the last term, we then take the tome spectrum of this replete bar construction of M that I defined up there, viewed as an object over pick S with the structure map that I also indicated here. So this then gives the working definition of topological Hochschild homology for 3 log EK rings with K at least 2. So this is very good. But luckily, there's a little bit of time left. There's still one piece of structure missing that I should also explain. We're interested in topological cyclic homology. And so I didn't say anything about how cyclotomic structures come to life in this game. And this is indeed kind of a little bit subtle. So again, if you're like super optimistic, you would hope that kind of you can commute topological Hochschild homology and taking Thom spectra. Topological Hochschild homology enjoys cyclotomic structures. This kind of we know back from the first definitions, and Nikolaus and Scholze give a efficient and very flexible construction of this. But what is not true is that the cyclotomic structure maps on the topological Hochschild homology of a Thom spectrum in general comes from data on the Thom spectrum. So this is true for spherical monoid rings, but it doesn't carry over to Thom spectra. So they're just kind of obstructions for this. So with this definition, we are just stuck when it comes to the cyclotomic structure. So what's the solution? Well, the solution is to translate this definition a little bit. So what you can also do using this definition here is you can view the Thom spectrum over S of this spectrum of this kind of map psi group as a pi naught of M group graded E K-ring in this generality. So, well, what you just do is you say, well, if I kind of choose a component here, the piece that is that sits over that component, well, it's just in that diagram, the piece that sits over that so in if you have the group completion here, it goes down to pi naught of its here, and you have this map here, and you just say, okay, I kind of restrict this to its different path components, and then this gives a pi naught of M group graded object. And now in a paper by Antio, Matthew, Morrow, and Nikolaus, so 4 people, not 3, they construct an extension of the cyclotomic structures of Nikolaus and Scholze in a graded setup. So what you then get is that the topological Hochschild homology, we give this a name with some star here indicating the grading, then the topological Hochschild homology of this graded object. So this is pi naught of M group graded cyclotomic E K-1 ring. So this, as a graded object, still has a cyclotomic structure, but now you can do the following. You do exactly as in the case of the replete bar construction. You first restrict this pi naught of M group graded object to an object that's graded over pi naught of the monoid, and then you don't want to consider this as a graded object all the time, so you can just take the underlying total object, and this then defines the topological Hochschild homology of this this object here as a cyclotomic spectrum. And what we show along the way is that this definition here is exactly equivalent to the term that I put down here. So so this is one of the things that we show in our paper, is that this is the same as the Thom spectrum of this replete bar construction of M, and then with the structure map to pick S. So while this definition here is very nice for computations and for motivating why this is the right answer, we can also use this definition and then get the full cyclotomic structure, which is super useful. And in the one generator case, a kind of a similar approach to logarithmic topological Hochschild homology and topological cyclic homology also appears in work of Ausoni, Baindia, and Molinos. But kind of this has nothing to do with kind of the number of generators, so this is then kind of quite general and allows to give us kind of a general definition of this logarithmic topological cyclic homology. The hard work is then in kind of actually constructing these localization sequences and showing that, for example, the maps you get there are compatible with the cyclotomic structure maps. So there's some work to do that clearly exceeds guessing the correct definitions. But I won't explain this now. And I was actually thinking of giving you at least one sample calculation. So we haven't kind of yet done the full calculation for the fraction field case. So this is still subtle because we need to identify the maps. But for example, one can actually write down how these localization sequences look like for the topological cyclic homology of this Thom spectrum over S of psi 2D. So this is an free E1 ring on a 2D dimensional sphere with its E2 structure, and then kind of this log structure that you get tautologically. So in this case, we can actually kind of explicitly determine how the logarithmic TC looks like. So it's not that it's completely inaccessible, but it stays subtle. That's to be expected. OK, thanks.
Questions? Yes, please.
Do you use Thom spectra over rings R that are not the sphere spectrums?
Yes, I didn't. I kind of suggested this, but I didn't explain it. That's a good question. So the reason why we are using this is, so we don't take the R-based topological Hochschild homology, because for general R, that wouldn't even enjoy a cyclotomic structure. So when we work based over R, we always forget to the underlying ring spectrum. Still, it's good to keep the R in mind, because this gives us THH of R or TC of R module structure on all the objects we define. So if you kind of take an R module and forget to the underlying spectrum, you still have an R module structure. And if you take the THH of an R algebra, or rather its underlying E1 ring, then you have a THH of R module structure. And it's these module structures that we care about, and that we hope to come out helpful in computations. Yes?
And are you also computing like the multivic filtration TC of this?
This is high on our wish list. So this is, of course, where it gets interesting. So with kind of looking into the motivic, syntonic, or whatever variants of this, and we have high hopes, but no results yet. Yes?
So in the infinity case, you have this log TAQ. I mean, now you're stuck with EK or EK minus 1. Can you do EK version of that?
This is actually something we haven't tried. I'm somewhat optimistic, but we really haven't looked into that. We're kind of so happy to have freed ourselves from E infinity.
Any questions? Oh, that's fine.